Nucleophilic substitution reaction SN1 and SN2. This is today's lesson. In this lesson we are going to learn definition of nucleophilic substitution reaction and mechanism of nucleophilic substitution reaction. So let's go to the detail. The first point is definition of nucleophilic substitution reaction. Let's see. When zinc is treated with copper sulfate, then zinc substitutes copper from copper sulfate to form zinc sulfate and copper. Another reaction, zinc plus sulfuric acid. Zinc substitutes hydrogen from sulfuric acid to form zinc sulfate and hydrogen gas. These reactions are called substitution reactions. Definition is the reaction in which one element substitutes another element from that compound, then the reaction is known as substitution reaction. When this is nucleophile, then the reactions will be nucleophilic substitution reaction. Let's see examples of nucleophilic substitution reaction. In organic chemistry, nucleophilic substitution reaction involves alkyl halide and aqueous solution of alkali like sodium hydroxide or potassium hydroxide. Let's see nucleophilic substitution reactions. First of all, 3-degree alkyl halide, CH3, CH3, CH3. This is chlorine. Its name is 2-chloro-2-methyl-propane. When this compound is treated with alkali potassium hydroxide, then nucleophile produced from potassium hydroxide substitutes chlorine, and chlorine is eliminated as nucleophile. So here one nucleophile is added to this compound and another element is eliminated as a nucleophile. Addition of nucleophile, removal of nucleophile. Let's see what is the product. CH3, CH3, CH3OH plus chloride ion. Now let's see definition of nucleophilic substitution reaction. When the substitution reaction is done by nucleophile, addition of nucleophile, removal of nucleophile, then this reaction is called nucleophilic substitution reaction and it is denoted by SN. Here N is a kind of subscript, nucleophilic substitution. So the reaction that is completed through substitution by nucleophile, this reaction is known as nucleophilic substitution reaction. Let's write another example of nucleophilic substitution reaction. Here this is 3-degree alkyl halide. Now let's see nucleophilic substitution reaction of 1-degree alkyl halide. Here CH3, H, chlorine. When this is treated with aqueous solution of potassium hydroxide, then This nucleophile substitutes this nucleophile. Here addition of hydroxide ion as nucleophile and removal of chloride ion as nucleophile. Then the product is CH3OH chloride ion. So this is a kind of nucleophilic substitution reaction as well, because here one nucleophile hydroxide ion substitutes another nucleophile, that is chloride ion. Here this is 3-degree alkyl halide, because the carbon which is linked up with functional group, that carbon is linked up with 3 carbon atoms. That is why this is 3-degree alkyl halide. But in this case, the carbon linked up with functional group, that carbon is linked up with only 1 carbon. That is why this is 1-degree alkyl halide. Now let's see mechanism of nucleophilic substitution reaction. Mechanism for 3-degree alkyl halide and mechanism for 1-degree alkyl halide. And through the mechanism, let's try to determine which one is SN1 reaction and which one is SN2 reaction. Let's see mechanism now. Mechanism for 3-degree alkyl halide. It involves alkyl halide and alkali aqueous solution of potassium hydroxide. Let's see the steps one by one. First step, potassium hydroxide produces nucleophile. Step 2, 3-degree alkyl halide. Here electronegativity of carbon is 2.5, chlorine is 3.0. Because of the electronegativity difference, the carbon chlorine bond undergoes heterolytic fission and this entity is formed: CH3, 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 this carbocation and chloride ion. At the second step, 3-degree alkyl halide undergoes dissociation and as a result 3-degree carbocation and chloride ion are formed. This is 3-degree carbocation. The positively charged carbon is linked up with 3 carbon atoms. That is why this is 3-degree carbocation, which is formed from 3-degree alkyl halide. We know that 3-degree carbocation is stable carbocation in other carbocations, like 3-degree is more stable than 2-degree, then 1-degree. Let's see step number 3. At step 3, this nucleophile combines with this carbocation. Nucleophile plus 3-degree carbocation, positively charged. So this nucleophile attacks this carbocation and as a result this compound is formed. Alcohol, tertiary butyl alcohol or 2-hydroxy-2-methyl propane. It's a kind of 3-degree alcohol. Another step we can write is step 4. This chloride ion combines with potassium ion produced at step 1 to form potassium chloride. Now let's look at step 2. From the step 2, 3-degree carbocation is produced, which is stable carbocation. The stability order is 3 degree is more stable, then 2 degree, and then 1 degree. Here, step 2 is slow step because from this step, stable carbocation is formed. That is why it is slow step. This slow step is considered rate determining step. But the next step is fast step. This is not rate determining step. Step 2 is rate determining step. In the rate determining step, we see only one reactant is involved, that is alkyl halide, not nucleophile. As only one reactant is involved here, only one reactant, that is why this substitution reaction is called nucleophilic substitution unimolecular SN1 reaction. Here, rate of this reaction depends only on one reactant, molar concentration of one reactant, that is alkyl halide. That is why this reaction is called nucleophilic substitution unimolecular, which is SN1. Definition of SN1 is when the rate of a nucleophilic substitution reaction depends on the molar concentration of one reactant, then that reaction is called unimolecular nucleophilic substitution reaction or SN1 reaction. As the rate of the reaction depends on only one reactant, that is why this reaction is called first order reaction. This is the mechanism of SN1 reaction, unimolecular nucleophilic substitution. Now let's see mechanism for 1 degree alkyl halide. Mechanism of nucleophilic substitution reaction for 1 degree alkyl halide. Let's write. Step 1, aqueous solution of potassium hydroxide produces nucleophile. Step 2, 1 degree alkyl halide. 1 degree alkyl halide undergoes dissociation and forms one degree carbocation and chloride ion. Here there is a difference between carbon and chlorine. That is why this dissociation might occur. But here step 2 produces 1 degree carbocation. 1 degree carbocation is not a stable carbocation. We know 3 degree carbocation is more stable, then 2 degree and then 1 degree. 1 degree carbocation is not a stable carbocation compared to 3 degree carbocation. As a result, actually this step doesn't occur because in the step unstable carbocation is formed. That is why this step doesn't occur. Then what occurs? Let's see. Here nucleophile attacks 1 degree carbocation directly. The OA is electronegativity of chlorine is 3, carbon is 2.5. So this bond is polarized. It becomes partially negatively charged. Carbon becomes partially positively charged. Now, a situation is created for nucleophile to attack this partially positively charged carbon. Then we get nucleophile. A new bond is going to be formed. Oxygen carbon, new bond. And this old bond, carbon chlorine old bond, is going to be disappeared. Here other groups and atoms are hydrogen, methyl group, hydrogen. This intermediate state is called transition complex. Now, in the transition complex, this is partially negatively charged, this is partially negatively charged as well, but this one is partially positively charged. Now, a new bond between oxygen and carbon is formed. Here hydrogen, another hydrogen, and methyl group, and this carbon chlorine bond is totally disappeared to form chloride ion. Step 2, nucleophile attacks carbon of alkyl halide and alcohol is formed, which is ethyl alcohol, and this is 1 degree alkyl halide. Another step we can write, chloride ion combines with potassium ion to form potassium chloride. Now let's look at the step 2. Step 2 is rate determining step. In the rate determining step, we see nucleophile and alkyl halide. Both the reactants are involved. That is, 2 reactants are involved here, and nucleophilic substitution occurs. This is bimolecular nucleophilic substitution. In case of 1 degree alkyl halide, in the rate determining step, 2 reactants are involved in the nucleophilic substitution. As 2 reactants are involved in the rate determining step, that is why this reaction is called bimolecular nucleophilic substitution. The definition is, when the rate of a nucleophilic substitution reaction depends on the molar concentration of both alkyl halide and nucleophile, 2 reactants, then the reaction is called bimolecular nucleophilic substitution or SN2 reaction. That is, SN2 reaction, 1 degree alkyl halide undergoes SN2 reaction properly, then 2 degree, then 3 degree alkyl halide. For SN1 we can write, we learned that 3 degree alkyl halide undergoes SN1 reaction properly, then 2 degree, and then 1 degree alkyl halide. This is order of reactivity of alkyl halide. Order of reactivity of alkyl halide for SN1 reaction is 3 degree alkyl halide, then 2 degree, then 1 degree. and after that we can write methyl halide. And order of reactivity for SN2 reaction is firstly 1 degree alkyl halide. Before 1 degree alkyl halide we can write methyl halide. After 1 degree alkyl halide, then 2 degree, then 3 degree. That is 1 degree alkyl halide undergoes SN2 reaction properly. This is all about SN1 and SN2 reaction. If this lesson benefits you a bit, please subscribe to the channel. No more today. Thank you very much.